Let's now solve a similar problem, which is also related to accessing the middle of the list, but slightly different because now we are defining a mutator method. We want to modify the structure of the list that we're given. Let's take a look. So the problem is we want to insert a new element, of course, since we're talking about a list storing string values. So we want to add a new string value at the index I in the list. And I'm going to give you two hints before you actually pause the video. I highly recommend you actually pause the video for this one over here. This one will really trigger some good thoughts about how you manipulate the structure of a singly linked list. Let's take a look. So hint number one, you want to notice the valid condition for the condition for I to be valid, right? Of course, I should be the smallest I you can take would be 0. That's the smallest valid index. However, notice that here we don't really say I should be strictly less than list.getSize anymore. We're also including the possibility of I being equal to the list.getSize over here. So what does that mean? That means it will be okay for you to say I want to insert a node at index list.size directly. For example, let's say if you got 10 nodes in the list, in that case I want to insert an index 10. So what does that mean? 10 is not even a valid index because the largest index for a 10 node list will be 9. So what does it really mean? I want to insert at index 10. That means I want to insert the new elements as the last node. And that last node should really become a new tail of the list, right? That's the rationale. And you want to keep this in mind. I will definitely illustrate when I trace the code later. But you really want to make sure you understand why. In this case, why are we including the equality as the valid condition for I, right? That's something you want to notice, which I already explained verbally. And hint number two, you may just want to think about using the getNodeAdd as a helper method. You may want to think about it, right? You can get around without using it just by declaring by writing some loop on your own. But it's really something that's duplicating the efforts by the getNodeAdd. Why not using it as a helper method, right? That's my suggestion. And also you may want to think about, would it be possible to really implement this method over here, which I'm going to give you the header for the method. Is it possible to implement this method just with the tail reference? Remember, we got a tail reference pointing to the last node in the list. Would it be okay? That's some question to think about as well, which I will also ask you again when we do the last operation later. Okay, all right. So think about these two hints, and then of course, this method should really appear as part of the singly linked list class, and this will be the header, the signature for the method. Add at index I and also some string element E, right? So I over here should be in between 0 and also list.getSize inclusive in both ends, right? What does that mean? That means if the size is n, how many possible values do we allow for I? That should be n plus 1 from 0 all the way to n. So that's why it's n plus 1. And it's going to be a mutator method, so we don't really return anything. We just want to modify the current chain of nodes that's being pointed to by the head. Right, you can now pause the video and try to sketch your solution. Treat this as an interview problem that you're given. How would you actually address different cases, like an empty versus non-empty list? And also, how would you handle the different values for I? And also, how can you really avoid reinventing the wheel by maybe using the getNodeAdd method as a helper method? Or can you even use the tail reference as a last node? Would it be possible, right? All right, you can now pause the video. All right, assuming that you did it, let's now take a look. Okay, let me just tell you one thing first. For this particular method over here, you can actually not use the tail reference because you simply don't know like how close I might be to the end of the list. Even if you know, in that case, the tail reference, the tail node, the last node over there, the only reference you have is to its next, which is null reference, which is useless for you to really go to any previous node. However, you want to keep this thought, hold this thought if you had it, because when we introduce the extension to singly linked list later, we're actually going to introduce like a so-called previous reference as opposed to next reference for each node. In that case, knowing about the previous reference would be very beneficial if you try to do the algorithm starting from the tail node. That would be possible, but not for now, right? That's something you can maybe make a note yourself, and then I'm going to reiterate later. All right, so that's our method here. Let's now go over again the line by line, and then the line, the code, the fragment of code itself for the algorithm is also very simple, only a few lines of code, but it does say quite much when we did the tracing. All right, so first of all, we want to say if I is either negative, right, or it's larger than size. So this is a different condition if you compare this condition against the one for get node at. I'll let you do the comparison. Okay, so we are saying that I is either negative or I is strictly larger than the size, but I can be equal to the size, right? As we said, when I is exactly equal to the size of the list, that means we're inserting the element as a new last tail node into the list, right? What about the else part over here? The else part, we're gonna distinguish between two subcases. Either when I is equal to 0, what does it really mean when I is equal to 0? When I is equal to 0, that means we simply want to insert the new elements as a new head node, basically, right? That's what we want to do. So that means we somehow conceptually we want to shift everything currently in the list to the right by one position. But shifting in singly linked list is incredibly cheap in this case, and also in many cases. We'll see. Okay, but just keep in mind, if when I is in extreme case, when I is the smallest value possible, in that case, it will be as if we simply want to add the E as the first node. That's what we're going to do. Okay, for this at first, I'm going to just show you the effects visually without tracing that from scratch. So you can simply go back to the at first operation, which we discussed last week. All right, so let's now talk about the else part. The if part is when I is equal to 0. Of course, the else part, which I haven't really revealed, is about when I is not equal to 0, meaning that I is strictly larger than 0. What's going to happen in the code over here? Before I show you the code, I would like to give you some conceptual sketch about what we really want to achieve by the few lines of code, which I will show you in a moment. I think that's more important than showing the code itself. Let's now switch to iPad over here. Let's have some visual discussion over here, right? So we are still talking about inserting a node at index I, but we are assuming that I is actually larger than 0. In the case where I is equal to 0, we simply add first. That's what we just discussed, right? So now we talk about when I is larger than 0, meaning that we are now trying to insert in at least from the second node and onwards, not just the first node, right? Let's now have the idea over here. If I is over here, right? Remember, I will be larger than 0. Meaning that I is larger than or equal to 1, meaning that the second node onwards. Right, you should really know the context over here. So I could be the second node, or it can be the third, can be the fourth, and etc. Right? But I would suggest we also got the previous node over here, which will be the node at index I minus 1. Because I is larger than or equal to 1, I minus 1 will be larger than or equal to 0. Agree? That's also important for you to note, right? It's very simple math. So I minus 1 will be larger than or equal to 0, meaning that such node does exist. It will be maybe the first node in the case where I is simply just a second node, right? It definitely exists. Of course, in the case where I minus 1 is actually equal to 0, in that case, we don't really have any node before that, but just in general, right? This part over here can just be the head reference, or maybe if I minus 1 is equal to 1, for example, in that case, this will be the next reference from the node as index 0, etc. Right? Right, so that's the general context we can have. We can think about I and I minus 1 is simply some in the middle of certain chain over here. Right? That's how you can think abstractly. And also, we're talking about the element E is simply pointing to some string. What we want to do is to really insert a node over here somehow, so that after I minus 1 node, the I node after insertion should be a new node that we're going to create, and then the data object should be pointing to E over here, which is the arguments over here, and then that node over here should really pointing to over here the old ith node. So the node that used to be at I position should now be I plus 1 position, right? So being shifted to the right by 1 position. And then the I minus 1 the next reference, rather than pointing to this old ith node, it should now be pointing to this new node over here. That's kind of the conceptual sketch. Let me repeat again by really drawing it. Okay. So what we really want to do is we want to create a new node over here. Okay. Let's call this maybe just the new node. The new node is pointing to this node over here, and for the data objects part, it's going to point to this particular string, right? So that's the parameter e or argument e, that whatever string value it is. All right, and what we want to do is we want to somehow insert this node into the middle over here, such that so the I-1 node wouldn't change. It's still I-1, but the ith node is going to become the purple one, and the I+1 node will become what used to be the ith node, basically, right? And here's my question for you. In order to really achieve what I just described, do we really need the I-1 node? Do we really need it, or we don't need it? That's a very important question. Let me write it down. Okay. Question over here. Do we need the reference to the I-1 node in order to achieve what I just described visually, right? It's a very important question that I would like you to think about first before I tell you the answer, right? If you don't think it's necessary, then you are claiming that by just having the ith node, I will be able to achieve the insertion, which I just sketched. That's if you say no. If you say yes, that means this will be necessary. All right, you can now pause the video and think about it. In case you don't really know what I was trying to ask, you may want to rewind the video. Maybe you just got distracted by something else, right? I think the question was posed very clearly. All right, so the answer is yes. And it's very important to know why. Okay, let's say this. Let's say we don't really know the reference to the node at I-1 index. Let's say we only have this. If we only have this node over here, it would be okay to really set the new nodes next to be this. But now the problem is, by only knowing the reference to the ith node, how can we set the I-1 next reference to the new node? So this is the part that's actually that cannot be done just by having the reference of the ith node alone, right? That's very important for you to know. All right. Do we need? We definitely need it. All right, because we want to make sure not only that the new nodes next will be the new nodes next will be what used to be the ith node, but also we want to make sure what used to be the I-1 node will actually now will point to the new node its next node. So these are the two things we want to do, right? Let me write it down. All right, so two things we want to achieve over here. Okay, number one. Let me do step by step. The I-1 nodes next is set to the new node. Right? So how can this one be done? Let's do it right away. So you can see I-1 is over here. So rather than its next reference, rather than pointing to what used to be the ith node, we're now letting it point to this new node over here. That's step number one. What about step number two? Step number two, the new node. The new node's next is set to the old ith node. I kind of did this sequence intentionally just to show you if you write your code in this way, it's not going to work. Because right now, notice what's happening over here. If I try to do this one first, I already changed the next reference for the I-1 node. In that case, how can I set the next of the new node to be the ith node? Because currently, you can see this pointer has been deleted already. There's no node, there's no reference that's really pointing to this ith node. So I'm basically lost. The chain has been broken and I can no longer locate this I node anymore. Hopefully you can see that I did it intentionally, right? So if you really want to implement code, you have to make sure it can execute sequentially with which will achieve your intended outcome. But if you do this followed by that, it's not going to do it. All right, that's very important for you to know. So what should we do? What we should do instead is to really reverse the sequence. All right, how do we reverse the sequence? Let me just really make a note over here to say this is not going to work. This sequence over here has a good intention, but this sequence over here is not going to work. Okay, this sequence of code does not work. Okay, I better keep this over here so you can really see that is a reference over here. All right. All right. So what will work? What's gonna work is I'm gonna put it over here, right? I'm gonna put it here. All right. Let's now do it again. What we want to do, and at the same time, let me just get rid of these pointers over here. But you definitely want to remember what I put in the orange over here is something that wouldn't work. And don't be too surprised. Maybe in the test or exam, I might give you this wrong version over here and then ask you to explain why it wouldn't work, right? That's something you want to keep in mind. And let me just delete this. Let's now do it again. So what we should do is we want to make sure we set the next of the new node to be the I-1th node's next first before we wipe it out. That would be the idea, right? Let's now write it down. So number one, we want to say set. How about this? We say the new nodes next is set to I-1th nodes next. So this is exactly what you will see when I show you the code, right? So how do we achieve this one here? You can see the I-1th node, the next one is actually pointing to here. So we want to make sure the new node's next is set to that same node, right? So we're going to do this. Okay, that'll be the first step. And what about the second step? The second step, now we can actually try to wipe it out. That's what we can do, right? So the second step would be I-1 node. I-1th nodes next is set to the new node. All right, let's now do it. And what's going to happen is, rather than pointing to over here, we are wiping that out, which is okay because we have already set the next of the new node to be ith node already. So that chain hasn't been broken. All right. So what I'm going to do is I'm going to say this next is going to point to the new node over here. So that's exactly the sequence you would see actually in the code, which I haven't really shown to you yet in the slides. But it's really important to see why this will work. All right, let me now highlight it. And then there might be, there's one thing I want to annotate as well. But before that, it's really important for you to see that this is the working version. Okay, so this working version. This is the working version. Of course, you'll be absolutely critical for you to know why this version wouldn't work, right? Conceptually. But of course, you can translate this into Java code and then try to run it in the debugger and see exactly why you will create some broken chain, which you definitely cannot fix, right? All right, final thing I'd like to remark is after this insertion, after we have done this, what's going to happen is the I-1 node remains to be at I-1 position, but this purple node becomes I, right? It will be the ith position. And what used to be at I position here becomes I+1, right? It's so important to really see that. That's exactly how the add node add is supposed to behave. So now we got I-1 and also followed by I and followed by I+1. Right, so really try to review this conceptual sketch, which will be so critical. If you really understand it, in that case, understanding the code should not be any difficult, right? Should not be too difficult. Let's now move back. And And you will see the 3 lines over here is exactly what we just said, right? First of all, create a node, find a node before I minus 1 position, which will be get node at. So that's why we can use the get node at as a helper method. Get that node first, right? So this step here is to find out what this reference is. Okay, you can think about this reference here will be, let me just put a reference over there just for your convenience so you wouldn't forget. So this is node before, right? And then this one over here, okay, let's just go line by line. Node before, and then we're gonna try to say the new node, create a new node, and the new node's next should be the ith node next, right? That's what we did. And then after that, we're gonna say the node before, over here, the ith node, the node before, which is this node over here, and its next should be the new node, right? Exactly the second step over here, right? It has the one-to-one correspondence indeed, right? And that's it. Of course, you don't want to forget, since size is the attributes that we declare. Remember, we trace the space for time, so you want to make sure if you actually increase the size of your linked list, in that case, you must increment the size by 1, right? You might be wondering, what about this branch over here? Do we need to increment the size by 1? We don't need to, because if you look at the definition for at first, itself actually will increment the size when necessary, so you don't need to worry. It's only this part here that we don't really call any other method as a helper method. Well, only this one over here, but that one there wouldn't impact the size, would it? So that's why we have to make sure this line here is so necessary to make sure you increment the size accordingly.